Okay, good morning. So we continue the topic of metric spaces. The first thing today we want to talk about, yesterday we talked about open sets and interior points, interior of a set in a metric space. Because it's quite fresh, let us start a new lesson without refreshing anything, okay? So we want to talk about now closed sets. So this is definition 4.1. So let us say that X and V is a metric space as usual. And then F is a subset of X. Yes? F is said to be closed. Okay, you have an idea of what is a closed set. I told you yesterday a closed set is the one that has a fence around it somehow, and open is the one that doesn't have any fence around it. Yes? So, for example, if I have this set what is your intuition? Do you think that this set that I have drawn in the standard Euclidean space should be a closed set or not, according to the definition of the fence and things? Yes? So this is because it contains the fence. If it doesn't contain the fence, I will draw it, but I put this border, the boundary in the dotted form. Yes? So, do you know what is the complement of a set? The complement of a set is every element in the set, in the universal set here, the X, which is not here. So it means that outside F, which we denoted by F complement. It means that this is the set X minus the set F itself. So if this set is going to have this border, if I look at the complement, do you think what happens for the complement? Do you think the complement will have some kind of border around it? No. Do you agree? Because these borders will disappear and not so the F complement will be outside this without this border. So if you imagine that one will be an open set. And that is the motivation of defining. That was just the motivation, okay? But if you want to define it, we say that F is closed, is said to be closed if F complement, which is defined to be X minus F, is open. So somehow, closedness is also defined in terms of openness. Yes, if a set, we say that a set is closed if its complement is open. That's the definition. And I try to make this understandable a little bit by this drawing the picture. But at the end, this is the definition you have to see. So one remark is important. In mathematics, open and closed are not opposite in the everyday sense. That's very important to understand in topology here. A set can be open only, closed only, both open and closed. I have seen sometimes in some math books they call it clopen. It's closed and open. And neither open nor closed. Okay? And I have written something down below. It's important to know in any metric space, the empty set and the space X itself are always both open and closed. Okay, but I want to explain this a little bit here. Let me see what is the next example. Yeah, so let me first talk about the last step here. If you have a metric space, so a little bit about remark 4.2. What I want to say is that, of course, you know that the empty set is a subset of X. X itself is always a subset of X. Okay, so let us go back to the previous lesson. Do you think that the empty set is open or not? This is always, you have to think a little bit. Why the empty set is open? What was the definition of being open? Every point in it is an interior point. Okay? If this is not to be an open set, it means that there is a point in it which is not interior. but it doesn't have any point. This is the reason that the empty set is open. Because if you say it is not open, it means that you could find a point in it which is not interior point. But you cannot find any point in the empty set. So because of that, we say it is vacuously true. So it is true that the empty set is open. So empty is open because of my explanations that I didn't write it here. But then immediately, what can I say about X? Do you agree that X is empty complement? Yes? So this means that if empty is open, its complement is closed based on this definition. So this means that X is closed. Is that right? Okay. But why empty is closed? Why empty is closed? I look at the complement of empty. So the complement of empty becomes X. Okay? And then X is definitely open because every point in the set itself is an interior point. Do you see? Do you see what is going on? Okay, so let me explain it a little bit again. So empty is open. Do you agree with this sentence? Okay. Because if it is not open, it means that you could find a point in it which is not interior, but that's not possible. Okay, let me ask you, do you believe that X is open? Because every point of X is an interior point. Yes, do you agree? Because if you choose any point there, I can definitely, so if I choose any point there, I can find, because the neighborhoods are subsets of X itself. Yes? Because let me choose one point in X. Can you give me a neighborhood which is definite neighborhood of X which is contained in X? So for example, if I write n of 1x, yes, what is this? This is the set of all points in X such that d of p and x is less than 1. Yes? Do you agree by definition it is a subset of X? Because you are choosing P from X with some extra conditions. So this set is definitely are chosen from X itself. Yes?
But does that also include if it's the empty set? In that case, because the empty set is a subset of X.
No, what I'm saying is that if I want to show that something is open,
yes,
I have to show that every element there is an interior point.
Yes, but why couldn't it be a border point?
Pardon?
Why couldn't it be a point on the border? How do we know for a fact?
No, we don't even know what the border of X is.
Yeah, that's what I mean.
No, but you don't need to think in that way. So what I'm saying is that pick one X there,
yes,
and I claim for you that the neighborhood centered at X with radius 1 is a subset of X.
Okay, yeah, sure, because it could also be the empty set then, right? Technically, it's possible, but empty set is also a subset.
Yeah,
of X. Yeah, okay, that makes sense.
Yeah. No, but this cannot be empty because every neighborhood contains its center.
Yes, yeah.
Yes, because for example, if X is in X, this P can only one possibility for this choice is X itself, and it fits this equation because the distance between X and X is 0,
yes,
and it is less than 1. Okay, so this is a neighborhood which is contained in X. So this means the point that I chose is an interior point. But because this point was an arbitrary point, it means every point within X is an interior point. So this means empty is open vacuously. X is open, for example, because of this argument. And now if empty is open, according to this new definition, its complement, which is X, is closed. And because X is open, its complement, which is empty, is closed. So empty is both open and closed. X is both open and closed. Is that right? So this can happen. In a metric space, a set can be simultaneously open and closed. Understandable or not? Okay, so let us go to the next example. This example is probably very clear for you. In the Euclidean metric space R, show that the closed interval is closed, but the half-closed interval is not. And of course, how do you analyze this? Why do you think that this set is closed? I mean, intuitively, we don't have that much time. These are simple exercises. You can make them precise at home, yes? So why do you think that this set in Euclidean space R is closed? Of course, you know that. What is the name of this in mathematics? We call it closed interval. Then I want you to understand that it makes sense even in the metric space. So if I call this F, and then what was my space? According to the example, the space given to me is R. So I want to see if it is closed or not. What should I do? I need to understand what is the complement. But can you tell me what the complement is? So if this is the R, let us say that here is A, here is B, okay? And then this is my set. So I want the complement of it. So what will be the complement?
It's open
from minus infinity,
yeah, to A open union.
A open from here to here, but A should be excluded because A is in the set. Union,
and then open.
Yes, B to infinity. And hopefully you see that this is open. But I want you to understand, if you want to prove this is open, you have to show that every point is an interior point. But that is very easy to understand. So this is indeed closed. So this is open. So this means that F is closed. Okay? So now, what about the other one, for example? Let me call it F1. A and B. What do you think about this one? It is not open. Why? Because B is not an interior point. Yes? If I take B as the center and look at any neighborhood, which means any interval around B, so some part of it will be outside.
Is this the other way around? That A is in an interior.
No, I'm saying that B is not interior.
Yes, but isn't A the one that, because if we had that...
A is not even in my set. If an element is not in my set, it cannot be an interior. Interior should be a subset of my set. Yes? Understandable? Okay, so this is not open. F1 is not open since B is not interior. Yes? And then F1 complement is what? F1 complement is -1. This one, union. But this one is not open. Yes?
Because A is included. Right?
Yeah. So this means that this is neither open nor closed. Not open. Why? Because this one is not an interior. So this means that F1 is not closed. Okay, so now let us go to the next one. Yeah, that's a good example. Actually, we did this one more or less yesterday. Well, I want to talk about, this is a multiple choice question, so one of them is correct. So if you consider the Euclidean space R, the set of real numbers, what can we say about the set of rational numbers? Is it closed, open, both open and closed, neither open nor closed? Yes, so example 4.4. So X is R here. My set is the set of rational numbers. Do you remember what was the interior of this one? Yesterday we talked about that. What was the interior of the Q?
It was empty set.
It was the empty set, which is not equal to itself. Yes? So this means that Q is not open. Because if it is open, its interior should be equal to itself. So Q is not open. Okay? But is Q closed? To answer if a set is closed or not, so far we have only one thing in hand, and that is its definition. So what do I look into it? I will check the Q complement. But what is Q complement? Q complement is the irrational numbers. Yesterday I showed it with this one. But do you think the set of irrational numbers is open? Why not? Because the same reason. If I ask you what is the interior of I, it was again empty. And it is not equal to I itself. So if the interior is not equal to itself, it means that set is not open. So this means Q complement, which is equal to I, is not open. So this means Q is not closed either. Okay, so this means Q is not closed. So which one we have to choose? Number 4 is the correct answer. Okay. But this is an important property. I want you to remember it. What is the property of open sets? If I have an arbitrary union of open sets, the new set is still open. And I have written arbitrary in red. For the second one, the natural question is that what happens if I intersect them? The interesting point that you have to be careful about is that if I have a finite intersection of open sets, it remains open. If I have infinitely many open sets and I intersect them, it might be the case that the answer is no longer open. Okay? So if I want to explain it here for you, by the way, these notes are also available, but in a different format, but the numbers are the same. So number 4, so let me at least see a proof of it. So what do I say in part I? I am saying that if I have a collection of open sets, for example, this is an indexed family of open sets. For every alpha, O alpha is open. The claim in part 1 is that if I union all of them and is open. Yeah? And part 2 is telling that for intersection you have to be a little bit more careful. So let me also write it for every alpha in A. We know that. And then we want to prove that that's open. For part 2, what we have is a finite number of open sets. For example, O1, O2, up to On are open, are all open. What we want to prove is to prove that the intersection of OI, I goes from 1 to N, is open. And I hope that you can feel the difference. In the union, it doesn't matter what is your index set. Is it finite? Is it countable? Is it even uncountable? So if you have any index family of open sets and you union them, it becomes a new set. That set is open. But for the case of intersection, you have to be careful that what you can guarantee is the intersection of finitely many open sets. And then the question is that, can you give a counterexample that if I go beyond finitely many open sets, this result does not hold? The answer is yes, we will see that as well. Because this is the first main theorem that we want to prove here. So let me try to understand that. So the proof of I. So I would say for simplicity of writing, let me write let O be that set instead of writing so much. So let me write it like this. We show that O is open, but you help me. I want to show that O is open. What should I do? So I start with the sentence let. What should I do? I want to show that a set is open. I have to show that every point in the set is an interior point. So I would say let
X belong to O.
the P belongs to O. Yeah. We show that P is an interior point of O.
So N epsilon.
We show that there exists an epsilon greater than 0 such that the neighborhood of that point with that particular epsilon, yes,
Is a subset of.
exactly. So that's it. Everything is clear, so we are setting up the basis for the proof. Okay, but now what do I have in my hand? I have P belonging to it. So I start from here. P belongs to O. So this means what was O? O was that guy. So P belongs to the union. So you have to remember something from the first lesson in analysis. So can you tell me what, or second lesson? So what can I conclude? If something is in the union, what does it mean? It means it is in at least one of these sets. What is the meaning? It means there exists an index in the index set such that P belongs to O alpha. Do you agree? But now, what type of set I am facing? It's an open set. So what can I conclude? I can conclude there exists an epsilon greater than 0 such that what happens, N of P, epsilon is a subset of O alpha. Yes? But do you see we are done? Why? I was trying to find an epsilon. I am claiming that the epsilon that I was looking for is the same epsilon that allows me to write this for this open set. Do you see why this is the case? Why? Because O alpha itself, so let me write it like this. On the other hand, can you guess what I'm writing? On the other hand, O alpha and O. What should I write here?
Subset.
Subset, yes? Because O alpha is one of these sets here. You are unioning them and call the union O. So each one of these individually are subsets of this one. So this will be like that. Do you agree? So, okay, so now we are done. Because therefore, so from number 1, let me call this one number 1. Let me call this one number 2. And then I would say from number 1 and number 2, what do I conclude? I can conclude that N epsilon P is also a subset of O and I. Yes, is that clear? Okay, but proof 2, let us see what problem I have. I want you to feel it, okay? So what problem I have that I have to give up my ambition and go down to only finitely many sets to be intersected. Okay, so let us at least start with the same idea we have here. So if you don't mind, consider these two proofs different. So I would say let, again, O be the intersection of OI, I from 1 to N. Okay, we show that O is open. Okay, so you see everything is more or less the same, but I am proving it independently from this. So I would say let P belongs to O. We show that there exists an epsilon greater than 0 such that N, the neighborhood centered at P with radius epsilon is this. So it's exactly the same. Okay, so I start with the same, but you see why the proof is different. So what do you think I will do now? I will start from the assumption that I have. The only thing that I have is that I know P belongs to O, but I'm waiting for you. So P belongs to O means what? Can you tell me? O is the intersection this time. So this means that P belongs to the intersection. Do you remember what I can conclude now? Anyone else? Yes?
It's in every single one of those.
In every one of these.
Yes.
So how should I write it? It means that for all I in the set of 1 up to not n, P belongs to OI. Is that right? Because when something belongs to the intersection, it means it belongs to all of it. So remember, in the union, the quantifier will be, what was it? The quantifier is existential quantifier, but here it's a universal quantifier. Okay, but now can you see what is happening? P belongs to OI. Okay? And OI is open. Yes? So what can I conclude? The existence, so this means this is an interior point. The existence of what? Epsilon greater than 0 such that the neighborhood centered at P with radius epsilon is a subset of OI. Do you agree with this one? But I want to repeat this argument not only for every I. Okay? So if I want to do that, do you agree that this epsilon that works for O1 might not be the same epsilon that works for O2, might not be the same epsilon that works for O3. So because of that, it is not a good notation. So I would equip it with an index. Okay? So for any OI, you pick I. For that particular I can find an epsilon which is related to that OI. Yes? Yes.
Is it wrong to write for every O, or so like for every O there exists an epsilon? Like for every OI there exists.
No, I just want you to learn how to write it very compactly.
But okay, yeah.
So I just want you to know that in the previous case, I just wrote one epsilon. But here, depending on which OI I am working in, the epsilon will be might be different. Yes? So to give room for this opportunity for epsilon, I equip with an index I. Okay? Now, so it is not finishing the problem because now I want to find, so can you imagine what type of, how many, let me ask you, how many neighborhoods I have now? How many neighborhoods I have? I have n neighborhoods. One neighborhood for O1, one neighborhood for O2, but all of them are centered at P with different epsilon I. So if you want to imagine it, how do you imagine them? In just normal Euclidean two-dimensional space. These are concentric circles. Yes? These are, so if you go to a scratch paper, P is the center of all of them, but one of them is with radius epsilon 1. I don't know, might be this one is epsilon 2, who knows? The next one is epsilon 1, for example, and etc. Yes, this will continue. These are the neighborhoods. So I have n neighborhoods with apparently might be different radii, but with the same center. So if you want to visualize it, you can visualize it as concentric circles, okay? But you know that neighborhoods are not necessarily circles. We had some examples. Sometimes they are rectangles or something like that, or squares, things. So, but this is a good imagination. Okay, now I am looking for a neighborhood that I can guarantee it is inside, it is contained in O. Can you come up with that one?
The smallest epsilon I.
Yes. So because we know that each one of them is in the correspondence O. Okay? If I pick the smallest radius of all these radii, then definitely that will be the smallest one. The smallest one will fit to its corresponding O, as well as every other one. So I would say that let So this is the intuition, but you have to write it rigorously. Let epsilon, how should I define it? I define it epsilon to be minimum of all these epsilons. Okay? And that is exactly why I need finitely many. Do you see that? Because if I have infinitely many, then I will have infinitely many epsilons. And I cannot define the minimum of an infinite set unless it is guaranteed there is an infimum, there is a minimum. So that is exactly the reason we need them to be finitely many. Okay, so now this is well defined, and because all these epsilons are positive, definitely the minimum is also positive, and it can play the role of a radius. Okay, let this claim. Can you fill up the claim for me? What is the claim? The claim is n, the neighborhood centered at P, but with the smallest possible epsilon, is a subset of what?
Oh.
Is a subset of. Yeah? Okay, so how should I prove this one? A standard technique. I would say let x belongs to n p epsilon. We show that x belongs to O. Do you agree? Okay, how should I write it? X belongs to n p epsilon. Then what does it mean? It means the distance from x to p is less than epsilon. So this means that dx and p is less than epsilon 1 up to epsilon n. Do you agree with what I'm writing? Because if this number is smaller than epsilon, epsilon itself is smaller than all these numbers. So this means that all of them are true. But what is the meaning of the first one? The meaning of the first one means x belongs to what? Neighborhood of P with radius epsilon 1. Yes. So how should I write it down finally? And then, so let me see. Yes. Yes, that's correct. And then up to x belongs to n epsilon np. Do you agree? But n epsilon I is a subset of OI. If x belongs to this, then it means x belongs to O1. And you can continue and say that x belongs to On. So this means x belongs to intersection. But the intersection is called O. Yes? So you see what I am writing, my argument is completely independent from the intuitive image. That is important. I went to a scratch paper, got an idea, because it was not that easy just come out of the blue and say that I define epsilon to be like this. But if you can imagine that they are concentric circles, of course you can choose the minimum one. The minimum one is guaranteed to be in all of them. Is that right? Yes. And then from the motivation I got there, I could continue very rigorously. You see, every part of it is logical, independent of the picture that I have. So here. Any questions? So you see, it's more or less nothing, but writing these mathematical symbols one after the other. Okay. Okay. So let us go to the next one. Okay, so this is an example. Show that in a metric space, the intersection of infinitely many open sets is not necessarily open. Okay, and you come up with an example yourself. Think about intervals. Do you see what I'm telling you? I am telling you that in the first part of the theorem, I didn't care how many open sets I have. For union, I don't care. But for intersection, I care. The number of open has to be finite. it is possible that I have infinite of them and the union is still open, but it is not guaranteed. If I want to have the guarantee is that I have to have finitely many. Okay? So then if I want to give you an example, so this is example 4.6. So what should we do? We say that, for example, ON, consider it to be this open interval on the Euclidean space R. Do you agree that all of them are open? Pick n equals to 1, it is the open interval from -1 to 1, 2 from -1/2 to 1/2, etc., etc. So n belongs to n. So all of them are open. ONs are all open. But can you imagine what happens if I intersect them in your head? But you have to prove it yourself, okay? So I intersect them, n goes from 1 to infinity. So what I'm doing, I am changing finitely many to infinitely many, okay? So can you guess what will happen if I intersect them? It is not hard to guess, because I have this is 0, -1 over n is here, 1 over n is here. So if I choose n to be 1, it goes from -1 to 1. But if I choose 2, it will become smaller. If I choose 3, it becomes smaller. So they are nested into one another. So they are getting smaller and smaller. So what do you think? If I start intersecting infinitely many times, do you think something will survive in the intersection? Intuitively. But of course, in the exam, you have to prove it rigorously. Yes?
It's 0. Right?
It's the 0. Okay, and this one is not open. Yes? Do you know why this is not open? Because the only point it has is 0, and if I choose any neighborhood around 0, it will go outside my set. So it's not open. So it is possible that I have infinitely many open sets, but when I intersect them, it becomes not open. Okay? So that's also good to know. And then there is a similar theorem for closed sets. The closed sets are the other way around. If you have an arbitrary intersection of closed sets, it remains closed. But if you have a finite union of closed sets, it remains closed. Do you have any idea? I don't want to prove it, but the sketch of the proof is which rule in set theory? What is that? It's called De Morgan's law. Yes? So, for example, if I want to show that, so let me say that I have F alpha, so this is theorem 4.7. So here, F alphas are all closed. We want to show that the intersection of F alpha belongs to A, is closed. Okay, but instead of showing that this is closed, a sketch of it, this is actually the proof. The proof is just one line. If I want to show that a set is closed, I have to look at its complement. Okay, so I consider this. Yes, but what is the answer? According to De Morgan's law, this turns into union, and every one of them becomes complement. Okay? But what type of set is this? Because F alpha is closed, F alpha complement is open. And I have a union of open sets, which is open. Which theorem was that? Theorem 4.5. Is open. Okay, so you can prove the other one yourself. That's very similar. So it is the other way around for when it comes to closed sets. Okay, now we want to define a new concept, and that is the concept of a limit point, derived set, and isolated point. So let me define it here for you on the board. So let us say that X and D, a metric space, okay? A point P, not in X itself necessarily, a point P in X is said to be a limit point of, let me write E, a subset of X. I have a metric space, I have a subset of that, I choose a point in X, I say this point that I have chosen in a bigger set is called a limit point of E if there is a neighborhood. If there is a neighborhood of that P, so let me write it like this. If there is a neighborhood of P that there is no if there is if of E if every neighborhood of P has a point of E, it has a point Q of E which is not P. I should write that is not P. Okay. So what does it mean? It means that, so if this is the ambient set X, and then I have a set here, okay, I say a point P in E is called, a point P in X is called a limit point of E if every neighborhood of that P contains at least one element from E which is not P itself. Okay? So for example, if this is a limit point, okay, in the usual sense. If I draw any neighborhood around that, this neighborhood contains one point of E which is not P itself. So this point P is a limit point. This point P is not a limit point. This is a limit point, but this is not a limit point. Why? Because I can find a neighborhood around it which doesn't contain any elements from E. So P is not a limit point. So limit point cannot be very far away from my set. It should be more or less close. But this point, is this point in my set? No, because it is dotted. Okay? But is this point a limit point? Still yes. Because if I draw a neighborhood around, every neighborhood around that, then I will have a point in the neighborhood which is not P itself. So if this one is also a limit point. So the limit points are the points not necessarily in my set, but they cannot be very far away from my set. That is the intuitive idea of a limit point. So a point is a limit point if every neighborhood around that point, contains a point from my set which is not the center of the neighborhood, P itself. If that happens, we say that P is a limit point. But if I collect all these limit points, so for example, can you tell me by just intuition, if you want to show all limit points of this set that I have drawn, where do you draw it? What are, so by the way, is this a limit point? Yes? This is also a limit point. So it means because if I draw any neighborhood around that point, it contains the point from the set which is not P itself. So this is also a limit point. So can you imagine what are the limit points of this set?
It's every point in the set and on the border.
On the board, on the boundary. Yes, that's intuition is correct. So that's if you understand that, that's the meaning of the limit. Now, if I collect all limit points and write them in and put them in a set, that set is called the derived set. The derived set means the set consisting of all limit points. Okay? So exactly, if I ask you what is E prime in this picture, the E prime is this one, and inside it, that is E prime. A set containing of all limit points. But what is the isolated point? The isolated point is a point in the set which is not a limit point. That is called an isolated point. Understandable? Okay, and then I have written the ones in red. Pay attention to this. So if I say that, so I want you to understand that a limit point is not necessarily inside my set. It could be outside my set, but it cannot be very far away from it. What is an isolated point? An isolated point is a point in my set which is not a limit point. So it means that I can draw a circle around it without intersecting with the set itself. It is isolated. It is alone. Okay? Okay, so let us continue with one example, and then we go for the break. So this example, can you tell me, for example, here, E 4.9. So I have E equals to 0 and 1. Well, can you tell me what is the derived set? So let us analyze it. So if I want to draw a picture here for you, this is R, and this is 0, and this is 1. Okay? So, just intuitively, do you think this is a limit point? Yes, because every neighborhood around that will contain a point from my set which is not the point itself. So every point here is a limit point. What do you think about this one? Is 0 a limit point? Yes, because if I draw a neighborhood around that, no matter how small it is, it will contain elements from my set which is not 0. So 0 is a limit point. But 1, is it a limit point or not? It is not in my set, but is it a limit point? Yes. Why? Because if I choose any neighborhood around that, doesn't matter how small I choose, it will cut my set at a point which is not 1 itself. So everything from 0 to 1 is a limit. Yes.
But doesn't, if the neighborhood around 1 is the smallest possible neighborhood, so that it only contains 1?
No, we cannot have that.
Oh, right, because, okay, so it needs to be...
The radius should
Yes.
be bigger than 0.
Okay.
Yes.
Okay.
Yes. But of course, it depends on the metric.
Yes.
I am working with a usual metric.
Right.
So might be in the discrete metric, you are right. You have to be careful about those things. But anyway, this is also a limit point. But is this point a limit point? No, because I can find an interval around that without having extra element from my set. Is this a limit point? No. So can you tell me intuitively what are the set of all limit points? What is the derived set?
Closed interval.
The closed interval from 0 to 1. So exactly, the points that cannot be very far away from my set. Okay, so the next one is a little bit problematic. So I have this set, so let me call it F, to be 1 over n, the reciprocals of natural numbers, is a set. So if I want to write some of them, it is 1, 1/2, 1/3, 1/4, etc. Okay, I don't have time to completely solve this problem for you, but do you have any idea about what the answer of f prime is? For example, if I want to draw a picture for you here on the board, so here I have 1, here I have 0, here is 1/2, here is 1/3. Be careful, nothing in between is in my set. My set are only consists of points. 0 is also not there, yes? So, for example, do you think this is a limit point? don't get confused. So this neighborhood around that doesn't have any elements from my set, not from the axis. It should cut my set. My set consists of only of isolated points. So none of these points is a limit point. Because, for example, 1/2, if I make this interval from my set contains one element, 1/2, but I told you that, you see, I have written Q shouldn't be P. So it doesn't contain any other element from my set. It only contains the center. Center doesn't count. Okay? So for the same reason, is 1/3 a limit point? No. But of course, you might say that they are cramping into one another. Somehow one of them becomes, no, the distance between them is finite. You can make the distance smaller than that one. So none of the points themselves are limit points. But do you think the limit point, is there any limit point? For example, can this point be a limit point? Of course not. This is very easy to see. Can this point be a limit point? No. Yes? But there is one possible candidate to be a limit point. What is that?
0.
0. Because they are cramping, they are getting very close. 0 is not very far away from the set. Okay? But now, claim is this. This is the only limit point. Okay? Can you see that? The proof is not hard. I would say that let epsilon be given. There exists an n in n Archimedean property. That what happens 1/n is less than epsilon. Is that right? Okay, so then what? Then the neighborhood of radius epsilon around 1/n, around 0, contains this 1/n. Yes, contains 1/n. No, I have to show that for every epsilon this works. Yes, that's correct. You give me 1 epsilon, I am claiming that the neighborhood of 0 with the epsilon that you give me contains at least one of these elements. Which element? 1/n. What is n? The one that is 1/n is smaller than epsilon. Is that clear? Yes or no? Today you are confused, are you? Yes? Okay, so let us have a break here.